So today's speaker is Professor Stephanie Simmons. Professor Simmons received her PhD from the Materials Department at the University of Oxford in 2011. Her thesis, supervised by Professor John Morton, was entitled Creation and Control of Entanglement in Condensed Matter Spin Systems. After her PhD, Stephanie Simmons held fellowships at John's College in Oxford, and between 2014 and 2015, she was a postdoctoral fellow at UNSW in Australia. She's currently a professor at Simon Fraser's University in Canada, and Stephanie Simmons is a world-leading researcher in the fields of silicon quantum computing and photon matter interfaces, which is what we're very much looking forward to hearing about today. So thank you very much, Stephanie, for joining us. And with these words, the virtual floor is yours.
Well, thank you so much. Thank you all for coming to a talk when I know beers are calling. So thank you very much for a Friday afternoon showing up. It's 8 a.m. here, and we are just ready to get into it today. I'm really excited to speak with you about silicon color centers. I think the audience, this particular audience, just because of what's been growing at Cambridge for so many years, you will appreciate more than most what I'm able to share with you today. So there has been, let me just get this going. So there we are. So I'm speaking to you today as a professor at Simon Fraser University, but I do have two hats. I am also the founder and chief quantum officer at Photonic Inc. that is commercializing these color centers. And so what I'm going to be speaking to you today is about the academic outputs. The company isn't disclosing very much about what it's been up to yet. But the overall message is the same. And forgive me, I have a bit of a sniffle, and I know that's totally offside these days, but I decided to go forward with the presentation anyway, because it's relatively minor, so forgive me if I cough a little bit throughout. When I started at Simon Fraser, I went off in a different direction than most, because you won't have heard of the term silicon color centers, probably. It's not a term that's been widely used throughout the literature, because there was this massive disconnect between the color center community and the silicon spin qubit community. There's no Venn diagram overlap whatsoever. But in fact, that's, I think, the juiciest target for future quantum technologies. And that's why we're putting all of our eggs in that basket, as it were. And it's all operating off the following premise, right? When I started taking a look at different research directions independently, it seemed evident to me at the time that there'd be kind of working backwards from where we expect to be in 30 years when this technology is large scale and global. It's going to have a couple of key properties. One, it's going to be linked by telecom photons. You're going to need to be able to have distributed quantum computing and quantum internet applications, and that's going to have to be kind of baked into the basic architecture of the system. The second one is going to have good memory, because this is one of the lessons learned of classical computation. Memory just serves so many useful purposes that we're kind of at the point where we're going to assume that memory is going to be part of it. And again, these are axioms, right? So they could all technically fall over, but these are the axioms we're choosing. And the third one is silicon. And that one is much more around, if you can get it working in silicon, then you win. There's just too much infrastructure that if you get it working there, then it's going to be difficult for any other platform to compete, even if they meet the telecom and memory requirements. And so we went looking, and silicon is actually good for multiple things. It was already known to be one of the best platforms for quantum memory, which I'll speak to on the next slide. And it was, of course, known to be the best platform for integrated electronics. But what was also becoming clear at the time, about 2015, is that it's truly the platform of choice for integrated photonics as well. Now, that's not necessarily obvious. There's lots of different materials you can use, and it's still an active area of research to look at other materials, but they're all basically on silicon in some sense. And you could take all the passive components at a minimum and translate them into integrated components on chip, and usually end up with as good or better performance, depending upon the element. And the basic principle then would be to work with these layered, this is the standard silicon photonics platform. So you have these buried oxide layers, this silicon device layer, and you basically are printing, you're etching into the edges, and you're printing fiber optics on the chip. And so to have a platform that has phenomenal quantum memories, which I'll get to in a second, phenomenal electronic scaling and phenomenal photonic scaling, it kind of seemed obvious that if a solution existed, if we could find a good spin photon interface that could work with telecom photons, it would be great, because what you would do is be able to put it right in the middle of the mode, right? You put these whatever the color center is or the defect, put it right in this mode, and it could talk very efficiently to the photonics, and the electronics could kind of go around and drive what needed to be driven. So that's the vision. And maybe I'll speak to the quantum memory side of it a little bit, because this is how I got into this space. I wasn't a photonics person, to be honest. I was looking at the spins, and one of my early claims to fame was driving a spin coherence time out to a couple of hours. And that's, mainly made possible by silicon, not by me, right? It's mainly made possible by the fact that silicon is just such a clean material. There's a bunch of other physics that goes into it and why silicon holds onto quantum memory for so long. But a lot of it is to do with how well we understand silicon, but also how clean we can have it. So one of the outcomes of a completely different scientific objective had a huge impact on quantum technologies and quantum lifetimes, these coherence times. And it was called the Avogadro project. And it was used to redefine the kilogram according to a number of silicon-28 atoms. And the reason they chose silicon is because it's the purest thing we can make as a solid object as humans. It's crystallographically and from a defect perspective, it is just the cleanest thing we have. We've just been hammering on that for decades, right? So this crystal here, single crystal, the shavings of that, this is all a silicon-28 crystal, the shavings of that were used to really launch forward quantum computing applications, because silicon-28 as a single isotope has no nuclear spins. And so natural silicon, which can be made very, very clean, has a couple of nuclear spins that add to the source of magnetic noise, right? And so the Avogadro project wanted to have a single isotope to define the kilogram, but this silicon-28 material also got rid of that source of magnetic noise. And so what was left over was this semiconductor vacuum that had these phenomenal coherence times. And so this plot is pretty old, but the records still hold. We can hold on to coherent quantum information for a very, very, very long time. This is a whole bunch of different platforms, and we're going to have to update it pretty soon, I think. But basically what you want to look at is, it's ion traps and it's silicon spins. The outstanding one is these rare earth materials. You can get that, and they beat us by a factor of 2 the year after. But the other thing to mention here, and this axis here, of course, is logarithmic. And so these are like 3-hour coherence times. This is great. And that's really helpful for a network application where the actual amount of time matters. But the other thing that matters from a computation perspective, and which is why lifetimes matter here, is because it matters how many operations you could do within the coherence time, because that sets your native error rate for that system. Right. So if you're trying to do error correction, you really want to be in a regime where the native error rate isn't the thing dominating your system, because that's kind of an upper bound for all these error correction asks. So you really do want to be in like this top quadrant here from just a bare like large scale scalability perspective. So little old SFU was punching way above its weight in terms of this the quality of these quantum systems, and that's one of the reasons I came here. I got to work and join forces with Mike Fewalt, who has just known silicon for decades as a world-leading spectroscopist. And so, okay, these things look great from a spin perspective. How do we get them to talk to photons? The question is why nobody looked before me or us, or maybe there's a couple other things that are in the same time scale, but some other teams that have started looking at it at the same time. But it's kind of a mystery why teams haven't been looking at silicon for color centers decades ago. And it could be for a few reasons, but maybe this is indicative. So the defect on the previous stage of this slide that had 3-hour coherence times, that's a phosphorus defect in silicon. So it's a very standard defect in silicon. And it has optical transitions. They're not quite in the telecom regime. This is near 1 micron. And they have optical transitions that are excellent in terms of their line widths, right? So in natural silicon, you could take a look at the ensemble line width, all of the different phosphorus spins all contribute to this kind of luminescence, this line width. And if you get rid of the silicon 29, not only does it help with your spin lifetimes by getting rid of the magnetic noise, but it really cleans up your optical spectrum. Now suddenly you can start to see spin states. You can see spin states when you have, billions of phosphorus atoms contributing to that signal. These line widths are on the order of 60 megahertz. That's just phenomenal. So you'd think, okay, well, this is great. It looks like a good photon interface until you look at the quantum efficiency of these interfaces. And maybe that's why people stayed away from silicon. The quantum efficiency of phosphorus, of this particular optical transition, was really low. And a lot of that's attributed to the fact that it's an indirect band gap, but that's not the end of the story there. It just happened to be the case that this particular defect, and a lot of them, have really strong Auger recombination. For those of you who have gone through that condensed matter training, Auger recombination seems to dominate a lot of things. And I guess people just didn't bother go looking. But we did. So we started first looking, admittedly, we relaxed one of our axioms. We started looking at the mid-infrared rather than telecom, because we weren't aware at the time of any telecom opportunities. We were looking for something that had a stronger quantum efficiency, and what I mean by quantum efficiency, for those of you who aren't in this space, is the proportion of the time, or the proportion of the time that when the object is in the optical excited state, that it spits out a photon, roughly speaking. So if it spits out a photon like every time, that's a very, very high quantum efficiency. And that's the kind of object you want to have, because it means there's not non-radiative processes that are going to get in the way of any kind of strong interaction with light. Because of course, if you want to have a good spin photon interface, that optical interface, that's the thing that makes or breaks your technology. So we went hunting for something that looked to have potentially a stronger photonic interaction. And we started by looking at selenium. And selenium is a lot like phosphorus. And you can use the periodic table as a rough guide here. So the reason why phosphorus gives you an unpaired electron, a good spin to use as a spin qubit in silicon, it actually takes the place of a silicon atom, and it has one extra electron by virtue of being in the next column over. So it's very much like a hydrogen atom. If you instead substitutionalize selenium or sulfur or tellurium, they form a double donor, so-called double donor, which means that you actually usually get 2 electrons, additional electrons, compared to the background lattice. But you can ionize it. You can set your Fermi level, or you can play with charge states to ionize that selenium. And an ionized helium sure looks like a hydrogen atom, right? So the picture there is that it would have orbital transitions that you could then use. And that's exactly what we found. So it has these 1s, 2s, 2p, kind of like, you can name them that way. We have some additional structure within that, which gave rise to these relatively strong, but admittedly mid-infrared optical transitions. So these are orbital transitions, and orbital transitions, you would expect them to have a higher quantum efficiency, and they did. This one was in the couple percent. So again, a couple orders of magnitude, but not really what we wanted. But it did give us the kind of luminescence properties. It started to seem right. Like you could see that it was emitting spin entangled photons. You could have absorption, that kind of thing. It was encouraging. And it certainly opened up the realm of opportunities for us, because what we hadn't yet gotten into was the whole world of silicon defects that have been studied since the 60s. And that's one of the best parts about silicon, is that if you want to know anything about it, you can usually, so long as you have a subscription to the old papers from the 60s and the 70s, it's all there. It's all been studied to death. So you can literally look up dozens of papers on a particular subject that they've already done that legwork for you. And so what we did is, this work really opened up that world for us. We started taking a look. And so I'm going to ask if there's any questions yet. Are there any questions yet?
So there's one question that has come through in the chat, and it's someone asking, so there are 2 questions to it. So the first part is, what exactly is your quantum system or your qubit in the silicon materials?
Oh, I'm getting there. I'm getting there. So that's why I was asking here now, because I'm about to get
Okay,
into
and then there is a little follow-up to that question that if you're getting there, maybe that's relevant to kind of address then. So if you are dealing with electron or hole qubits,
yeah.
how do you deal, could you comment on how you deal with valley degeneracy?
Yeah. So we are not doing the traditional dot stuff. We're not working with interfaces. Valleys don't concern us at all. And I can get into that at the end, but this is basically, these are defects far away from interfaces. And to answer the question about electron or hole, we are restricting our interest to those which have naturally unpaired electron spins in their ground state. So I'll get into it. So yeah, the punchline is that the future is all about T centers. We're not there yet. I'm going to just kind of walk through like the other kinds of centers that you have, because this is really a whole untapped area. Silicon color centers, there's really like only maybe one or two other teams that are now finally starting to look at it alongside us. There's just so much to do here. And it's partly to do with the timing. So silicon damage centers are kind of the name that you want to look for, because people were looking at silicon in the 70s and the 80s to understand what the natural defects that formed within silicon were, as a means of understanding silicon that would be operating, say, in space, right? So they would be, or in nuclear facilities or whatever, right? Like you'd be wanting to understand how silicon behaved under these environmental conditions. So if you go looking there, there's buckets of information about what these defects are, and these are luminescence centers. So they just didn't go by the name because they were studied in the 80s, not after the advent of quantum computing, essentially, or the prospects thereof. So these are naturally forming defects, very much like NV centers in diamond or any of the other defects in any of the other semiconductors. They're formed by natural constituents in the lattice, but you can also implant ingredients. And there's a whole wide array of them. They just go by different names. Our first work into this was a couple years ago, where we took some of that magic silicon-28 and we damaged it through electron radiation and neutron radiation. And then what we did is we took a look at the defects that were forming naturally. And you see, these are right in the telecom region. So we just went right to the axiom of choice and the axiom for telecom here, and just took a look at what was naturally forming. And this is in ultra clean silicon-28, and even still it formed these radiation damage centers, these really easy to form ones. The punchline for these ones, which I'll kind of skip through a little bit more, is these are all brilliant emitters, but they don't have an unpaired electron spin that would be suitable for easy spin photon interfacing. There may be indirect means of getting at, say, a nuclear spin, but I'm going to not talk about that today. But they're definitely at some interesting wavelengths. So we have something right in the telecom region. The G center is almost impossible to get rid of. It's such an easy to form defect. And it's everywhere. And when we went from natural silicon and looked at it in silicon-28, we got to see all this additional structure, which again, it's not magnetic, sadly. We were really excited about that for a second, but it's not magnetic. And then the W center is another one. And now there's separate teams that are looking at all of these defects now for quantum applications. But again, these are really should be thought of much more as emitters rather than spin photon interfaces, because there's no really natural, not easy way of getting a spin photon interaction, but they definitely have good photonic properties. The rest of this talk is going to be on the T center, which is the defect that we're most interested in right now, although they're from a family of defects that do have kind of exactly what you want, right? They have telecom access. They seem to be relatively efficient. The quantum efficiency is relatively high, and they have good spin properties, and they seem to be easy to form. So the rest of this talk is going to be all about the T center, but there's a family of them, the T, I, and the M centers, and there's maybe 3 or 4 others we've since discovered, all kind of work in this category. And so there's quite a bit of work, room to play. So the T center, okay, as a structure, what it is, it's 2 carbons and a hydrogen. And again, this forms naturally, right? So this was a known center from the 70s and the 80s that formed under certain annealing and damage conditions. So we didn't have to start from scratch. There was put forward that there was an unpaired electron spin in the ground state. It wasn't actually resolved in the literature before we got started, if that was true or not. There was conflicting reports in the literature as to whether or not it had an unpaired ground state electron, and it does, which is great. So we took a look at it in silicon-28. So we followed the kind of older recipes, and you can compare the natural silicon and inhomogeneous distribution to the silicon-28. It goes through this dramatic narrowing again, which is phenomenal. What we learned is it's a Debye-Waller factor, or the fraction of the light that's in the zero photon line, and it's about 23%, which is great. It also wasn't known in the literature, relatively easy to hack down. All of this, this is like a big paper that we put out a year and a bit ago now. And it has a lot of work on the spectroscopy of T centers in bulk materials. So if you want to know a lot about this as a defect in kind of a pristine bulk crystal environment, that's where you want to go take a look. And it also has all the possible references that you'll want to dig up from the 70s and the 80s. Basically, we referenced everything we knew of at the time there. So, my computer isn't progressing. So you might ask why. Oh, so something's freezing there. Yeah, let me just speak to this for a second. So you might ask why we picked the T center. This is 1326 nanometers. Let me see if that'll play now. Let me see if it'll go through. There we go. So you might ask why we would take a look at the T center when I said that there's a family of other opportunities. And one of the reasons is that this is right in the O band, and the O band is like around 1310. That is the single mode infrastructure in all modern data centers. So that's good. And then this, like, exactly, single mode fibers is around O band, which is phenomenal. And it's also the zero dispersion point for said fiber. So from a long distance perspective, there's just a couple different things. It's also easy to make, but this is the one that we're pushing on the most quickly right now. Yeah, there's something going on here. Forgive me. Let me try that now. Okay, so what's the actual structure of the center? So it's an excitonic optical transition. And so what that means is that the ground state, which I alluded to, has an unpaired electron spin, which is great. And it also has nuclear spins for the hydrogen and the carbons. Now, the excited state, what is this transition? So this is the 1326 nanometer or 900 MeV or so. That goes to an excited state, which we'll call the TX state. And that is an exciton. So you're adding an exciton to the system, and an exciton is an electron hole pair. And so the electrons form a singlet, right? So the electrons form a singlet, so they have no more magnetic contributions, but you also have this unpaired hole now in the excited state. So the excited state here as a whole in silicon, that comes from the valence band. Basically, it's a 3/2 object. So it would have 4 levels ordinarily, but that can be relatively sensitive to strain. And so what we actually have in the defect is a pair of levels in that first excited state, in that TX level, which we've labeled TX0 and TX1, and it's split by a couple, just under 2 MeV. Now, that means that around 2 Kelvin, you can kind of ignore TX1 entirely, which is wonderful. It means that you don't get any thermal activation, so you don't get any thermal broadening. Nothing's in the way, so you can really just think about T to TX0. And both of these have 2 levels within them, so you can kind of think of it as a pseudo spin 1/2 to spin 1/2 transition. Nice and easy. The lifetime of this thing is in a Goldilocks regime. So it's around a microsecond, which means if you ever want to put this thing into a cavity and purcell it, which you would want to get rid of the sideband anyway, you can then push it down to the couple nanosecond regime and not have to worry about picoseconds. But it's not too long-lived that it's too dim to see, right? You have to start with something. So for us, it's a little bit on the long side for the Goldilocks regime, but we're really happy with this time. Now, we have a bit of, the level structure on this thing can get quite complicated. And that's because it is not a simple substitutional defect. There's a lot going on in this center. It has 3 nuclear spins, 3 atoms, and that means just the cost of doing business to having so many qubits, right? In every defect, we have 3 nuclear qubits and 1 electron qubit if we choose to in every single one of these, reliably with the same interaction. That means there's a bunch of different orientations. So we have 12 different magnetic orientations. It's actually 24 that come in pairs, but you have 12 different orientations of this defect with respect to an arbitrary magnetic field. So fortunately, the ground state, the electron spin, doesn't seem to care what orientation it's in. It's an isotropic G factor, so that means you have the same kind of Zeeman splitting regardless of which center it is. But the excited state, that hole, cares a lot about what the orientation of the magnetic field is. And so you can see 12 different, it's an anisotropic G factor. So basically you have 12 different splittings in the excited state, which means for this pseudo spin half to spin 1/2, each of which have 4 optical transitions, which you could tap, right? That means you have 4 times 12, 48 optical lines that you're looking at, right? In an arbitrary ensemble. Okay, we can manage it. It's all known, right? We didn't have to invent any of this. Like a lot of the work on the spectroscopy of this stuff had been done, a lot of the early work, but you could add to it. But it is you have to know how to navigate that. What you don't get optically is, of course, all the substructure from the nuclear spins. So it's really this electron spin which is giving rise to this direct spin photon interaction, because you can drive specific spin states, electron spin states. So, okay, 48 lines. This is how it looks. So we have, you start off at 0 field, everything's one really nice, sharp, really, really ultra sharp single peak. And then you split that all out and you can actually pick which orientation you want to talk to. And so here we've color coded the different orientations so with the A, B, C, D transitions for each of them. We say 11, we actually have 12 here. They're just, you haven't quite broken out this level here, this one, A, B, C, D, that one actually has 2 contributions to that signal, which you could guess by just looking at it. So yeah, quite a bit, but you can go and take a look and then do spectroscopy on each of those centers. Okay, so now that you have that spin photon interface, you can go and try and drive it resonantly. And we were very lucky to find out that these things can be driven resonantly, kind of indefinitely. They don't seem to blink. You can just drive them and they always return. And that's a big difference between the T center and some of those, like the G center in particular, that thing bleaches. So I was really happy to hear that, you don't seem to be able to photoionize. And you don't seem to have too much Auger recombination, but that's not for this slide, that's a different conversation. Right, so what you can do when you drive it resonantly is very, very quickly hyperpolarize it, right? So if you drive one of those optical transitions, here with the B transition, you're of course driving both of the nuclear spin states within that because you can't optically resolve them. So they're both getting pumped to that TX naught state, and it's coming right back to the other electron spin state. It actually could come back to both. There are branching ratios, but very quickly it hyperpolarizes. So much so that if you raster a laser over top of it, you actually hyperpolarize more quickly than you get luminescence, right? So you actually only get a couple photons before everything goes and hyperpolarizes in a spin way. So you would only, if you drive it across, so the same sample that we saw on the previous slide, but you take a resonant laser and you drive over it rather than take a look at the total photoluminescence, you actually only get this one little center peak. And what you're getting here are the defects that actually have the same splitting in the ground state as the excited state, which means you don't hyperpolarize. So that's the only contribution that you see. Everything else is hyperpolarizing. So if you depolarize, right, if you're probing this with magnetic resonance in this instance, you can depopulate and start to recover some of the signal. And so that's one of the ways that you can use to tune up your microwaves. So you can start to see that structure again, and you can still pick which, you can optimize your microwaves to optimize the signal for one of the orientations over the other one. And so we did take a look at spin lifetimes in this one ensemble here, but we could have optimized and gone for orientation 11 just as well. And so that allows us to give a readout scheme, which I'll kind of skip through a little bit, but basically you can get spin readout this way. You can actually drive a cycling transition through the nuclear spin, and the details are in the paper if you want to go look. But the real conclusion is that these things behave like good spin qubits. And again, this is what you'd expect. What we see over and over in silicon is, especially for unpaired electron spins, the noise of those seen by those spins is usually dominated by the quality of the silicon. So it's dominated by the silicon 29s, or if there happens to be a whole bunch of other like lots of N-type or P-type defects or stuff like that. The silicon is the thing that makes the qubits good, and the defects just play within that realm. So we have good spin qubits, and we have, in this instance, a bad magnet, like we knew. And so we haven't done any dynamic decoupling or any of the rest of this to push this out to minutes or hours or the rest of that. We stopped. The T1 times are just like any other spin in silicon at low temperatures, like longer than you care to measure. For phosphorus at these temperatures and fields, it's like weeks. So T1 is never really the thing to push on. T2 is usually a magnet phase stability issue, and dynamic decoupling gets you most of the way there, but we just decided to get on with it. So yeah, these are Hahn echo numbers for the electron and the hydrogen. So this is going to be another break point when I asked for questions. This was a lot of bulk spectroscopy work. The next phase of the talk is going to be about integration and scaling of these things. But I would say what was known before we got started into this space was it was named a T center. And I didn't mention that earlier. The reason it's called a T center is because what they used to do is they used to just damage silicon across the board, and they never knew what they were looking at. So they just labeled them alphabetically. And then people would come in later and figure out what each of those particular lines meant, like what from the vibrational structure, what they actually were made up of. So that's why they're all the alphabet soup, but there's lots of different defects now. But yeah, that's the history there. So we're using that naming. They figured out back in the 70s and the 80s what the structure was, up to whether or not there was an unpaired electron spin. They knew what the wavelength was and roughly how to make them. We figured out all the rest from a quantum perspective, like what do you care about for a quantum application? And again, this is just part of all the details that's known. And I encourage you to go take a look at that paper if you care about the minutia of this defect. So that's actually a good place to pause for questions.
Yeah, great, Stephanie. So we have a question from Daniel Jackson, and he's writing, could you please expand a little on the origin of the splitting between the ±3/2 and ±1/2 whole states?
Yeah, fantastic. So it is to do with the actual native strain around a T center. So whenever you create one of these defects, the lattice has a very predictable strain pattern around it because of the defect. And that gives rise to a change in like I said, strain splitting for the actual valence band around it, essentially, and that's what the whole is seeing, right? So you actually get this inherent strain splitting, and you get different ones for different defects. So yeah, I hope that's the direct answer.
Okay, thanks. And then we have a question from Jesus, who's saying, overall, including inherent quantum efficiency, cavities, etc., what is the state-of-the-art fraction of radiative decay?
Okay, say that one more time because I want to make sure I'm answering the right question.
So
please.
Overall, including inherent quantum efficiency, cavities, etc., what is the state-of-the-art fraction of radiative decay?
Okay, so I'm not going to tell you is the answer, but especially because I know that this video is going to go onto YouTube after. We have been taking let's just say it's very encouraging, and I don't consider that at all a limiting technological issue, but it's certainly a lot better than anything else we've seen in silicon so far. So
okay, thanks.
I'm sorry to be cagey. I just know that this is going to go onto YouTube. So
no, I mean that's perfectly fine.
Watch this space. Yeah, we're clearly working on it, right? There are actual issues with performing quantum efficiency estimates. So we have given it a go. We have a whole bunch of lower bounds, but of course, as soon as you publish a lower bound, it's just going to be changed later. So we want to just nail it down properly, and that's inherently difficult to do. Having said that, we are very happy with the numbers that we have.
Okay, so a bit of a cliffhanger.
Yeah, sorry.
Yeah, that's okay. I think that's it for questions for now. But,
all right, cool. So let's get into it. Let's get into it. I mean, okay. Let's just say it's enough that people keep signing on at the company for a good reason. Anyway, okay, so sorry, that's a little bit cheeky. Okay, so we have, let's make these in devices, right? It's all well and good to be able to create these defects in a bulk ensemble and be able to take a look at their beautiful properties in that material, but these things are, natively forming defects, and it was unclear if we would be able to make them within the integrated photonics material that, I was saying is going to scale this whole thing. And so we had a go at it. And again, we were very lucky. We were lucky that these things seem to form really easily. And it could be because they're, of course, damage centers, so that when you damage the silicon, they form very naturally. So by implanting the constituent ingredients and playing around with some of the annealing conditions, you could find, very, very bright samples very quickly. And so, yeah, we were getting samples in our SOI that were brighter than our bulk, like millimeter size crystals. So that was very encouraging, and we went through it. And they didn't seem to be that sensitive to the damage, right? So it's, not perfect, but this is heavily, heavily damaged material. So here, these are the annealing conditions we were playing with. You got some really, really bright samples. That implant flux is actually rather high. We're talking about a couple 100 nanometers of silicon. That's a lot of damage in a very small space. But again, we could see the structure is the same. It's the brightest thing. Like, these materials are just incredibly bright. And the line width, the inhomogeneous line width of the material, actually, so it's shifted. Here we implanted carbon-13, so you expect the shift, which is great. But the line width wasn't so much bigger. So we don't have an inherent or rather the broader strain sensitivity is relatively low. And that's encouraging, because the thing that, as I kept getting into, the thing that makes or breaks this technology is really going to be its photonic interface. It's really going to be how pure those photons can be, or how strong that interaction can be in a cavity mode. And that will be determined by, how stable that frequency is, how well defined it is, all the rest. And this gets to the next one, which is, it's a big point. It's kind of the reason that you don't see silicon color centers in the news, really, in terms of a quantum computer, right? It's a good question to ask. We've been looking at, the royal we have been looking at color centers for decades, right? Why don't we have a really, really large scale color center quantum computer yet? And it is to do with this photonic interface. How do you really get these things to be uniform and have high quality? And so we wanted to take a look at the so-called characteristic spectral diffusion as a means of trying to assess the material quality or the environment quality for these T centers. Because we know that the spectral diffusion, which is the tendency of an individual color center to wander in frequency, right? We know that it's pretty good in silicon-28 in these bulk, like pristine environments, because we see these really, really, really sharp lines as an ensemble. And you can also look in and burn in and get really, really narrow lines. So we did this kind of characteristic spectral diffusion test where we swept a magnetic field and saw how quickly we can hyperpolarize as a means of doing a quick and dirty test to assess the quality of the material that we had. And so this top here is, we have a characteristic spectral diffusion of less than 30 megahertz. It's actually on the order of like 10 megahertz. And in measurements that we've done since. And that's true for the silicon-28 or the natural silicon. So these bulk crystals are on the order of like 10 megahertz or something in terms of total characteristic spectral diffusion, like long time, total wandering kind of spectral diffusion, not the instantaneous one, right? This is like the total wandering of any given defect. And when we did that same measurement in our SOI that we basically made near amorphous, we were getting something like a gigahertz, which, okay, improvements need to be made, right? But that's a starting point, and we've been iterating since. So that's the kind of starting point where you really want it to be about an order of magnitude less than that. But I will say that this is already, a lot better than what we've seen from many other color centers in devices, right? Devices just seem to have this interface quality, and different defects coupled to the different noise sources of different interfaces differently, as you would expect. And it seems like this is actually a really good starting point for basically having done zero optimization. We're already off to a really good point. And again, this was about a year ago, this data published about a year ago. Okay, So now that we could create buckets of these T centers, what we did was we wanted to go and take a look at them. And what you do in, when you look at other color center labs is you go and you make a cryogenic confocal microscope and you go and take a look at them. The problem with silicon is that what makes it, especially SOI, like the material that you use for integration, what makes it so good for an integrated photonics platform is that the light is a really high index, right? It's like 3.4. And so it really keeps the light inside that device layer. The losses aren't really high, which means if you're going to go take a look, it's really hard. And these things are already pretty long lived from an optical lifetime perspective. So what we did is we etched these pucks. And I'm not going to call them pillars. In Canada, we're going to call them pucks. They have the right dimension. They're little pucks. And we printed a whole bunch of them. We printed about 30,000 on this particular chip. And all the data from that is on the archive, again, about a year old now. But you'll hear that one in the news soon, hopefully. So these pucks, what did we do? We went and took a look at pucks, and we went and took a look at our T centers within these pucks and identified a whole bunch of individual ones. So this is a patch of 144 pucks, which had about 150 qubits that we could go and talk to, and you can name them. There's Natalie and Jane, and they go back and they're still there. You can go and do resonant excitation on them. So you can go scan a laser over top and see where they start luminescing. And that's great. You'll note that the count rate is really low, right? So these things are still, they're not per cell enhanced, right? So these things are just looking at the raw emission of individual ones. But yeah, that line shape is exactly what we are getting. The long-term, these are like long-term line averages for each of them. It was exactly what we were predicting from that kind of magnetic field characteristic spectral diffusion. We can look at all of the qubits and all the 150 qubits there and take a look at their position and their line width. And their line width was, exactly what that kind of material produced. So that's encouraging. You could also see that there's a distribution in terms of what the frequency was. And the reason why it's weighted to this higher side is that that's where the TX0 and the TX1, like that's the next level, it's higher in energy, right? And they start mixing. And so you'll start to get some interactions depending upon what the strain environment is for that T center, but it's not too much over what the bulk distribution was. So again, really promising. And we went and took a look at them. We did the G2 and we did all that stuff to go and convince that we have singles, but yeah, we can create these things kind of where we want. Now, admittedly, we put them everywhere and then etch down where we wanted to. But it's given that they're able to form within 200 nanometers, that gives you an idea of the kind of localization capability that you would have laterally as well, without showing you any data backing that up, but I'll kind of just say that out loud. If you want to go and take a look at individual spins and spin splitting, you can have an optical observation of spins in silicon for the first time, which is cool. The picture is here. We put all of those, the whole chip on a static magnetic field, a permanent magnet. And remember, the excited state splits differently depending upon the relative orientation of the defect to that arbitrary field, right? And so different defects in that same patch, they see the same magnetic field, but their orientation is different. So they're splitting, their excited states are going to be different. And so some of them have the same splitting in the ground state and the excited state. And so one laser can drive both of those transitions so you don't get that hyperpolarization, right? You remember that like if you drive just a resonant laser, everything will hyperpolarize too quickly. It optically initializes too efficiently, right? So what you can do is do a 2-color experiment and play with the lasers of 2 different frequencies. And so that's what these color patches are here. And so when the excited state is the same as the ground state splitting, then one laser does both, and you get this kind of cross in this 2-color map. But you'll start to see splittings when those start to change, and you start to see these kinds of peak splitting where you have to have different wavelengths for the 2 different lasers. And of course, there's going to come in pairs, right? Because you can either have them like that or that. And that will more efficiently drive the whole defect in a luminescence sense. And so if you expand that view, when you take a look out, you actually see all of the 4 transitions, not just B and C, but all of those 4 different transitions. And you can go and do the whole modeling and figure out, how hard you're driving and like lower bounds on different things. And it's, it's just nice to be able to go back and then you see it again and it's always there. And so it's really promising. as a technology. We're really excited about it. So yeah, I'll end it there because I was told that this was supposed to be a 45-minute thing, and I know there's been a few questions, but I imagine there'll be more in a bit. This is an outdated picture. There's more, even the outdated natives. So things are moving really quick. But this was all the stuff that I talked about today were really SFU results. And SFU research is really having a lot of fun with these systems. We're up at SFU Mountain, Burnaby Mountain, which is in Vancouver. Metro Vancouver, and you can some days on these inversion days you can look out over like it's really lovely. It's like you're on a mountain. You get to go hiking in the woods when you need a breath of fresh air, and it's really peaceful. And you can now look over a sea of clouds sometimes when you get these inversions, which is kind of incredible. Anyway, our labs are here, and although I didn't talk about it, we are closely connected to a startup called Photonic. Photonic has 60 people. This is from September. Anyway, things are going really well, and there's lots happening. So I thank you very much for your interest. You should continue to watch this space. Yeah, thank you very much.
No, thank you, Stephanie. This was a really great talk. Super exciting to see about all your results. So for anyone on the call, I see that we already have one semi-outstanding question that I'm going to read up, but if anyone else have any questions, please raise your hand, write them in the chat, or pop them under the Q&A button. But I'll start with this question that's come in the chat, and you kind of touched upon it in the last part of your presentation. I'll read it out in case there's
Sure.
other things you want to add. So overall, let's see, here we have it. Has optical single shot readout been achieved? As a follow-up, is electrical readout or electrical excitation possible?
Okay, so optical single shot readout of the spins, nothing has been published or disclosed. In terms of electrical readout and control, again, nothing has been published or disclosed. However, we do know one of the knobs that you have is electric field, and you have the ability to tune the zero phonon line electrically. That data will be disclosed first at ICPS in June. So there's going to be some work that we present there, but it's actually lovely. Like you can tune these things, and you know that you don't have that symmetry which precludes it, right? It has an actual sensitivity to it, which is you kind of have to be in a Goldilocks zone for that, because you need to be able to have relatively low spectral diffusion, which means insensitivity, but you have to be able to tune them around. So yeah, and then in terms of electrical readout, the picture is here. Optical is definitely more efficient, and electrical, you don't want to have electrodes really close to a photonic structure. So there are ways to do it. We haven't shown any data on that.
Okay, thanks. I see Hugo has his hand up, but just before I got another question in the chat, where an anonymous attendee asks, what would be the next big breakthrough in your part of the quantum information effort? So kind of what's the kind of next goal that you guys are working for? It's how I interpret this.
So there is there has been quite a fantastic set of breakthroughs around color centers and different kinds of color centers, different ways of scaling it up. But and so we can kind of use that playbook, and you can imagine what the milestones would be following that playbook. There are definitely cavities involved because you're going to want to have stronger interactions with the light. And so there's reflection-based schemes or emission-based schemes. And using either of those, you should be able to entangle lots of these things together. And so there's just a lot of opportunity to push forward on that, as well as pushing forward on all kinds of things like fidelities and lifetimes. And I mean, it's a whole effort to make this underpin truly the quantum internet, right? The quantum internet is going to be telecom. And I believe it's going to be silicon as well. I believe it's going to have these kinds of ingredients in them. So pushing forward to make sure that is possible, right?
Okay, thanks, Stephanie. So over to you, Hugo, for your question.
Yeah, thanks. So I have basically two questions. One is in terms of scalability of your actual quantum computation side of things. Um, so you show all these pillars. How do you expect the connectivity between multiple qubits to be? And do you have sort of multi-qubit operations with high fidelity that you could see scale across a large number of qubits?
Yeah, I can absolutely see it. I think one of the strengths of a photonic or a color center system is that you kind of don't need all of them to work. You can kind of, print a whole bunch of them and pick the ones that do work. And the pucks are to be cheeky, just a mere stepping stone. I wouldn't, that's not a photonic structure that was going to form the basis of any kind of larger scale. It's really just to go and see them. But you want to put in, there's silicon is the best place for cavities, for photonic cavities, really. Like the records are held there. And so you can really make phenomenal high yield cavities and put these things where you want them and put T centers in all of them, and then have really efficient coupling out and play with them that way. So the connectivity can be what you want it to be. This is by design, a high connectivity system, which for
But you connect through your cavities, you connect different
well, once the information's in the photon, once you've entangled the spin information with the photon, you can connect them however you want, right? Because photons aren't restricted in connectivity in the same way, right? So you can play all kinds of games. Yeah.
But so, okay, I mean, if say you have hundreds of qubits and you want to just entangle the lot of them in a single operation or in two operations, or very quickly just get the whole thing entangled, how do you imagine that happening? You get them all to go to photonics, entangle that bit?
I'm not gonna you're not gonna tease that out of me, sorry.
Okay, this is also coming.
Well, I mean, like, okay, there's just so much out there, right? There's lots of possibilities, and I have a clear view. View, but I'm not going to lay it out. No, sure. Sorry.
Okay, and my second question: you've highlighted the strengths of silicon a lot and how silicon is the future of a quantum internet. Given that we have other platforms for quantum computing, do you think this silicon-driven quantum internet would play nice with the other platforms, or will they become obsolete in the silicon-dominated quantum world?
Yeah, it's hard to predict the future on this. I think that if we push the metrics of T centers forward, or another color center, another telecom color center forward, I don't know what you get from interfacing it with other platforms.
Well, just if you want to communicate with other platforms, right? If you have a computer,
yeah, but it's like we can communicate, like, you know what I mean? Like these can communicate with the other T centers. So like, why would you, like, what do you get by talking to another one, right? Like if you can get the performance metrics up, then you kind of don't, the T centers aren't reliant on any other technology. The other technologies might become reliant on T centers for their communication, and that's cool, but that's not what I'm spending my mental focus. Like if the T centers could, like, if you can do everything you need to do, like linking lots of different, like, because it's going to be a distributed computing framework. So the distribution of entanglement across a distributed large scale quantum processor is going to be the bottleneck of anything you do, right? So if you can make that work with the same physics on chip and off chip, then why add more complexity? Sure. It's not clear.
I guess that's if you're convinced that your if can be answered by a yes. Yeah. Yes, we can do it.
Yeah, totally. And that's, you kind of have to operate on faith a little bit to see that you can push it. But I mean, silicon spins have demonstrated 4/9 fidelity for single spin control, for example. There's no reason why we wouldn't be able to get, again, phenomenal readout fidelity, single shot readout fidelity. Like, I don't see any major barriers to that. It's going to be all about that photonic interface, right? If you can really, really get that photonic interface up in high quality, and that if you can get it across the line, then
multi-qubit scaling as well, right? Because single qubit is great, but you want to.
But that's why the photonic interface matters so much.
Yeah. All right, great. Thanks. I don't want to take everyone's question time.
I see Crispin has a question. You're on mute, Crispin.
These impurity centers, you don't have any control over where they go. They're just randomly sighted in the lattice. So that means that occasionally two could be sufficiently close to one another that you might get some hopping of charge between them. Have you seen
Right.
any random telegraph signals or anything like that in your optical data?
No, not at all. And actually, that's one of the reasons why this is really nice, because famously within silicon, it's been really, really hard to get electron wave functions to overlap enough for them to talk to one another, right? Like this is the whole effort of UNSW for, you know, not just now, but like ages past, getting that wave function overlap and using that to drive some kind of Kane proposal. That's been hard. There's to do with the structure of the conduction band partly, but from a charge perspective that you mentioned, I mean, no, the answer is no, we haven't seen anything like that. So these densities are still relatively low where we wouldn't expect it. And also we kind of don't mind if one or two of them do that, but we haven't seen any signature of any of them at all.
Okay, thanks, interesting.
Yeah, no problem.
So I have a question here from another anonymous attendee. Or possibly the same
Everyone's so
anonymous
cagey.
and this person asked, as a non-photonics specialist, what kind of losses do you have when you transport telecom photons over long fibers? Could you use this framework to link up a silicon computer in, for example, Europe with one in China?
Great. So I will answer a question that wasn't quite asked there, because I think it's going in a really, really positive direction. So fiber losses are phenomenal for O band and C band. So these are the kind of, this is the reason why these are the telecom frequencies of choice. You can get phenomenally low losses, and we don't have to use anything different than regular single mode fibers. However, you do get photon loss. And so as a quantum entanglement distribution challenge photonically, you're going to get a couple 100 kilometers before it just becomes really prohibitive. And so if you want to do true long distance entanglement distribution, you're going to want to have places where you can purify or entanglement swap or do the whole quantum repeater game to get that communication pathway. You're going to need to have these, you can't use classical repeaters, but you can use so-called quantum repeaters. And that's, again, something that this technology could do really, really nicely, because it offers you that memory node and that local processing node that you can do to really distribute those communications. So it's not going to be a single hop unless you're using satellites and have long memories, right? Like that's kind of the longer term picture. If you can have long memories that can hold on to quantum information and that they can actually talk to different users across the globe, that's how you would do it, rather than through a single a single fiber going over large distances. But over short distances, absolutely, there's lots of demonstrations, and Europe is really pushing ahead on this in terms of network demonstrations with short hops. But if you really want to get to lots of users and lots of distance, you're going to need something with a kind of a memory spin photon interface infrastructure, something like what we have.
Right, thanks. I see we're almost out of time. We have 1 minute left before the hour is done. So I'm going to be cheeky and kind of steal the last question slot for myself. So I'm kind of interested in quantum metrology and things like this. And color centers have played a very important role in bringing the field of quantum metrology forwards. And I wanted to ask if you've thought about, or if your colleagues have thought about, if these silicon color centers could be used for any particular quantum metrological tasks, maybe before we have our quantum computer as a kind of, stepping stone towards getting there. Yeah,
so they're not good at room temperature. These are kind of 2 Kelvin objects, which are better than millikelvin, but they're truly like 2 Kelvin objects. I would say, so like the large bandgap, the wide bandgap materials definitely have a leg up from a sensing perspective if you're going to do anything at room temperature, right? So that's just, there's kind of no line there. However, if you're going to be doing a lot of distributed sensing challenges, like some of those large baseline telescope things that need entanglement over really, really big distances, it touches on the last question that we had, that basically you need something that can talk to telecoms, and then you can start thinking about those kinds of games. So it would be a niche kind of application, and it's not a central focus, but it would be a consequence of being able to distribute entanglement over larger distances.
Okay, Thanks, Stephanie. Thanks again. Thank you very much for being with us at this early morning hour over in Canada. And yeah, thanks for everyone who's been on the talk. Next week we're going to hear more about silicon quantum computing, but then in quantum dot-based system from TU Delft.